brownouts or blackouts. We have all experienced that one time or another. In fact, Bombay has been very lucky. We experience a lot less because of the way it is being divided unfairly in our favor. But what happens is the flow of power is through links of given capacity. So even if you have supply and demand matching in a very broad distributed fashion, individually the pipes may not be able to carry the amount of power required. That is another problem which has to be solved. We are actually quite well placed in the gamut of the countries where large amount of power is used. According to Power Grid Corporation of India Limited, we produced in 2011 about 163 gigawatts of power. You measure these things in gigawatts, and 163 was the number for 2011. I'll come to a number more recent. China, on the other hand, has 900 gigawatts of power. You may have seen some of these numbers in Professor Kakotgar's talk also. Now, why are pipes required to connect generators and generation points and consumption points? The reason for that is that the sources of energy, like hydro, which is available typically in the north and northeast of India, and thermal, which is in the middle part of India, are far removed from the load centers. Load centers are the consumption points. We are a big load center, so is the south, and so is the capital region. So these high tension wires carry high voltage based electricity from the from the generation points, which is here, to the consumption points, which is far removed from them. Okay, now you see why balancing has to be done between consumption and generation, and pipes are required for it. And there are different symbols here. You can look at the slides later on as to what other sources of energy exist beyond thermal and hydro. Now, this is what is called as a power flow diagram. Some of you may have seen this in your physics or electrical engineering classes. The pipes that I've been talking about are these pipes. And this gives you the carrying capacity. And this sinusoidal icon here stands for a generation point. So we have generation points at these two ends of the spectrum, and consumption points or loads at here and here. And the grid is divided into areas. This is area A, for lack of a better name, area A and area B. And often there is flow of electricity from one generation area to another consumption area. And like I said earlier, consumption should equal generation. So here consumption is 300 megawatts, and supply is happening from here, 200 megawatts of it, and 100 from here, from the same area. Who decides these flows? People who are sitting at various decision-making points. And this is another instance of the same flow. People are sitting at what are called dispatch centers, load dispatch centers, or communication centers. And these are hierarchical in nature. And we have, at the bottom level, substation or plant level sensor information. I'll say what the sensors are in a second. They send information to a district level decision-making authority called LDC, Load Dispatch Center, sub-LDC. And these collect their information, send them to state level decision makers, and finally at the national level. So there's a lot of planning that goes on hourly basis, 15-minute basis, daily basis. A lot of dynamics are taken into account in changes of the profile of consumption, generation, failures. But much of it is happening in a manual fashion. There is some what is called SCADA-based energy management systems which have multi-way information flow, but even there the time constraints are much larger than is required to avoid catastrophic situations. And our goal in making things smarter is to reduce this gap between when data is is produced about the flows and failures and state of the system, and when the decisions have to be made to respond to that situation. Okay? So the first motivation is something which is a dark point in our history, recent history. We didn't experience it as much, but I'm sure we all have relatives, friends, our own families in the north of India who are affected by this 500 million people disaster. And like I said, the state information is available, but not in real time. It didn't have the inherent smartness inside the system. The people who understood what was going on, but they couldn't react to it because the communication mechanisms are not there, and they couldn't exercise their options in time. But the failure of the northern grid is a major black mark in our electrical engineering history. And it affected some people for 2 days. You may see the brown area of the country. This is dark brown, which is affected for 2 days, the light brown for a day. So this is a recent history. Now, I don't know whether to be happy or not about the other fact, which is that such blackouts are not only confined to India. We can take some solace from the fact that power outages are on the rise even in developed economies, which is both a good thing and a bad thing. A lot of people are working on this problem, including from developed economies, and they may come up with solutions for this before we do, and force those solutions on us, which may be inappropriate. So it's important for us to catch up much sooner than we would normally do, because solutions from the West are usually more expensive than we can afford. So that's the first motivation. So let me pause here for a couple of seconds and see if there are any questions. No questions? Everybody is on board? Yeah.
Hello. Good morning, sir.
Please.
So this is Vinay here. You said the blackouts, even there are there in the developed economy as well, and therefore, say, good as well as bad at the same time. How come, I couldn't get how they can be good. How do you mean that?
By good, I mean that a lot of people are working on it beyond what is possible within India and other developing countries. The bad thing usually is that the companies are much faster at converting ideas into products and systems in the West. We are a little slow in that. So, whereas solutions may be developed as soon as they are required and is understood, they may be forced on us in ways which we are not prepared to use optimally, which is happening in lots of areas. Defense, for example, is a good example of that, where we are thrust certain things which we don't need or which has more than we need. They're not cost effective. So that is what I'm saying. There will be development, there will be advances, but whether it's best for us to use those same systems is a question mark which we'll never get to answer unless we also develop something in parallel and understand our real needs. I'll see if I can mention some of the nuances, some of the differences between what we need and what they have, or what they may have to offer, and why that is important to worry about. Okay. Any other point? Okay. So the first motivation understood, and if there are no questions, we'll go on to the next slide. How do you know there's a failure situation which is arising? Frequency is one of the first characteristics of electrical power, right? We all know about Indian frequency being 50 hertz, and the West has mostly 60 hertz and so on. So any deviation from this 50 number is an indication of something brewing. And in a synchronous grid, by the way, it means that every part of the grid is synchronized in terms of properties, frequency, voltage, current, and so on, with every other part of the grid. That is as far as I want to go. It's a technical term which will take a little bit of explanation. But just think about the whole grid being one uniform network, which is interconnected, and any part of the grid, if it goes into a chaotic situation, will have an effect on the rest of the grid. Okay, so it has to be done carefully. There are lots of reasons why things are being made synchronously. Again, we won't have time for that. But what I want you to remember is that generation and load must be balanced. I mentioned this before. And secondly, if that balance cannot be achieved given the generation capacity or the load requirements, then we have to control the generation, meaning put in some more generators into the circuit, into the grid. Or what happens in India typically, load shedding happens. This decision as to whether to bring in more generators depends on capacity which is idle and waiting to be brought in. It can't be brought in seconds. It takes a number of hours sometimes for a coal plant to be turning on one of its idle generators. Whereas solar energy, for example, is much easier to bring into the grid compared to coal plants. That's one of the reasons why people are working on them feverishly. Load shedding, again, the decision is being made at those dispatch centers which I showed you on the previous slide. Okay? We would like to do all of this decision making as far as possible in an automated fashion, informed fashion, decentralized fashion, reliable fashion, cost-effective fashion, and so on. That's where the smartness comes in. Here is a bit of a technical detail. All of you recognize this sinusoidal wave. Power flows, when it flows from one point in the grid to another, there is a likely shift in the phase angle. This theta I, compared to the peak, is likely to change. And like I said earlier, frequency implies a certain property of the electrical signal, and so does the phase angle. And of course, other things are current and voltage. That shows you the magnitude of the wave that we have here. To have decision-making possibility at a second level or sub-second level, we have to have a high sampling rate of this phase angle. The voltage magnitude and the phase angle together is called a phasor. Phasor. Okay? And the more synchronous the measurement, the more accurate the measurement of two phase angles, two magnitudes at two different points in the grid, the better we know about the health of the grid. Is this clear? We sample at different points in the grid, compare the phase angles, and the distance between the phase angles will tell us how good the synchronization is. It won't be perfectly equal because as a flow, there's a delay in the grid wires, the cables. So you can't have them perfectly synchronized. So a certain amount of deviation is allowed and possible. That should be understood. Now, how do you measure things synchronously? So to give you an idea behind the problem, suppose I look at the state of my room, my hostel room, a particular light. I want to know whether the light is on or off. I want to know whether the light is on or off by looking at both the switch position and, for redundancy, the light's illumination. Get the point? Two different measurements are being made about the same event, which is the lights being on or off. If I just sample the switch position and the light's illumination at two different points in time, and from that try to figure out what's happening, I might sample the illumination value subsequent to the turning off of the switch, which is fine. If I get it the other way, if I sample them at the same time according to the local clock. I get them transmitted to some centralized site, and they get switched along the way in the network. I might see that the switch is off, but the light is on. You see the point? You can play this mind game. So what we have to do is to timestamp the measurements using a GPS synchronized clock. You take both the measurements at the same time at a high time accuracy, with a high time accuracy. Once you do that, all the events will come together to you as a decision maker with the same timestamp. You wait for the timestamps to align themselves. You can figure out which is the state of the switch, what is the state of the bulb, whether it's illuminating or not, and create what's called a state estimation. You estimate that the switch has been turned off, the light is off, so everything is good. Yeah.
What is the sampling rate you are referring to?
This is...
And how accurate you want the timestamp?
Okay, that's the question is, what is the sampling rate and how accurate are the requirements? The more accurate they are, the better. But sampling rate today is 50 hertz. 50 samples per second.
Yeah.
It's not enough. But that is where we are starting the...
But what would be your requirement? What is your expectation?
See, there's no free lunch. So what I'll do is I'll give you some examples of queries or decisions that have to be made and how valuable they are in terms of decision making, and also the accuracy requirements in terms of time. There are enough requirements, enough queries or decision making requirements which demand 200 hertz, but the bandwidth required to process them is going to be very, very large. So one has to do a cost-benefit analysis and figure out how to position your design point with respect to frequencies.
This is primarily to maintain the synchronicity?
Pardon?
This is primarily to maintain the synchronicity?
I didn't get the first word.
Is the requirement dictated by the synchronous, how synchronous?
No, not really. Not really. It's a cost. If I just sample them, I have to use all the samples, otherwise it's a waste. And using them happens somewhere far away from the sensing point. And that communication will take some effort. But the point is that these PMUs, again, another key phrase I want you to carry away from here is phasor measurement units. These are these sensors which are quite expensive, but they give you precise monitoring capability on the health of the grid. And the more precise that information is, as we just discussed, the more clever or smart you can be in decision making, and precise as well. So I've been talking about frequencies as being a good health indicator. Let's look at what happened the night of July 30th, 2012 at 2 hours 33 minutes. 12 seconds into that minute, or until then, things were quite good. The frequency was close to 50, 49.65. You can't read it from the back, I'm sure. But then things started to unravel. There was what was called a separation. This is the grid containing these large number of high-tension transmission lines. And usually they have to be synchronized. The frequency should be about the same, with some deviation possible. Like here, this deviation is okay, except that this is far from the rest of the grid. That's what caused the havoc. So there was a problem, and there has been a committee which went into this disaster to suggest ways by which to avoid the repetition of this problem. Professor Anil Kulkarni, a colleague of mine from EE, was a member of the committee. He also has a lab which has the ability to track such phenomena in close to real time in his lab. And this is where I borrowed the data from. So what you see here is what is supposed to be a single grid separated into two grids, two subsystems. And if you're not prepared to deal with that phenomenon of separation, then things start to fail. And one failure can lead to another in a cascading fashion, which is what happened. And what happened was there was a breakup of the grid into the northern region grid, the western region grid, the eastern region grid. If you have seen the term cut set in your theoretical background of graphs, a cut set took place along this border. And in a nutshell, separation started 2 seconds. This is 2 seconds. 2 seconds from the disaster point. And later the generators tripped, meaning that they shut down. And this is the lower part of the graph. The upper part of the graph is Mumbai-related grid, subgrid. And that continued to operate. It's still around 50 in the frequency domain. So this generation capacity came down to a lower value, and then finally they all shut down here. The blackout took place. Okay? That is in sort of a very layperson's terms what happened. Frequencies started to deviate between different parts of the grid. And automatic shutdown mechanisms took over, closed the generators, and the rest is history. This is the same grid, same flow diagram that I showed you before. These are the transmission lines. These are what are called buses, or the points at which flow comes in and goes out. Junction points, if you will, or a terminus in the context of transportation systems. Flow of passengers into a terminus, they take other buses and go out in transportation systems. Here, flow comes in, is distributed according to plans created by the state load dispatch center. And if you have information from PMUs, which are synchronization happening through GPS satellites, then we get what's called a wide area monitoring system. Okay, that's another key word to remember. This is where computer science comes in and marries electrical engineering. Okay? So the state load dispatch center collects the PMU data along the lines of what I mentioned before in terms of this data collected, current, voltage, phase, and frequency, and a number of other things like positions of relays and switches and so forth. And this state LDC has monitors, like here, where there's a visualization of the current state of the network underneath that point. They make decisions which are locally possible. And then subsequently, any decision they can't make which has an impact on the rest of the grid, they send upstairs, like in the previous hierarchy that I showed you before. Okay? So wide area monitoring systems are considered to be primary ingredients of smart grids. So here is another picture that I wanted to take away from this talk. And that is generation, transmission, and distribution. Distribution now containing generation points. Why? Because windmills can be anywhere. You can even have a generator on top of your building. Some buildings are beginning to do that in the form of solar arrays. So generation can happen anywhere, including within the transmission system and the distribution system. That confuses things. Because right now, generation happens, not right now, till a few years ago, generation was primarily through large power plants. And everybody knew where the capacity, what the capacity was, and how much generation capacity is left after some failures and all of that. Getting the state of the network of the generation capacity was very easy. But now everything is everywhere. This is handled, or this is tamed, this problem is tamed by having these red marks, or brown marks as the case may be, which are monitoring points, some of which are PMUs, phasor measurement units, like the ones we saw before, some of which could be simple sensors, occupancy sensors inside dormitories or hostels, or room sensors saying is a particular room being occupied, and how. So what we have here is a power network, grid power network, showing generation, transmission, and distribution, with the monitoring happening continuously where the red dots are. So a smart grid, if you want to take a definition away from this talk, uses information and communication technologies to efficiently, reliably, flexibly, and sustainably monitor and control the generation, distribution, and use of electricity. Okay, so we are covering the whole territory of power generation and usage. Now I'm going to come to the second motivation behind smart grids. Now if you look at the capacity today, in terms of installed capacity, is 180 gigawatts. This is up from 167 we saw in 2011. Right? Installed capacity and existing used capacity are two different things. Some capacity might be idle because of failures or planned maintenance and so on. So usually it's less than 180 that is being generated. And much of it is made up of thermal and hydro, thermal being 2/3, hydro being about 11%, 21%. Fortunately, renewables are catching up slowly, but it's still only 11%. Renewables here mean wind, small hydro. For example, some villages have started, especially in mountainous regions, hydroelectric power plants, captive plants, biomass,